learner. I, Dr. Tarkeshwari Verma, welcome you all in this massive open online course of Fundamental of Engineering Physics. Before we started this lecture, tell me one thing. Everyone using rubber band in our home. Did you remember that? When you pull on the rubber band, it scratches and become longer. That means if you applied some force, they become longer, and if you remove that, they come their original shape. That means if you applied force, they become longer, and if you remove that force, they come their original shape. Can you tell me why that happened? Fast give me answer. Yeah, just because of material of rubber band is elastic. So today's our lecture topic is elasticity. Today we learn about elasticity, elastic limit, stress, strain and ultimate strength. Different type of modulus like Young modulus, shear modulus, bulk modulus and their examples. We solve some numerical also. Another example of elasticity is the bungee jumping. Long elastic strap which stretches until reaches a maximum length, that is the proportional to the weight of the jumper. The elasticity of the strap determined the amplitude of the resulting vibration. If elastic limit for the strap are exceed, the rope will be break. Let's understand elastic and inelastic materials. Elastic material have some special properties or characteristics. An elastic collision lose no energy. In a simple way, we can say that when two objects collide, they bounce each other without losing their total energy. The deformation on collision is fully restored. That means the object get squeezed or deformed when they hit each other. They go back to their original shape afterward. So, in an elastic collision, both the energy and the shapes of the objects stay the same before and after they collide. In an inelastic collision, energy is the lost and the deformation may be permanent. It means when two objects collide, they might be not bounce off each other completely. Some of their energy is lost, often as a heat, sound or by causing the object to get squeezed. Unlike elastic collision, the objects may not go back their original shapes and damage or deformation could be permanent. Restoring force. The restoring force is the force that acts on the deformed elastic object to bring it back to its original shape and size. It is always directed opposite to the direction of the deformation. For example, when you stretch a spring, the restoring force acts to pull the spring back there its original length. Next our topic is the Hooke's law. Hooke's law is the principle that describes the behavior of the elastic material, particularly spring, when they are stretched or compressed. It states that restoring force by the material is directly proportional to the displacement or deformation of the material which experienced by the material. Its change to the length. The mathematical formula of the Hooke's law is represented by F is equal to minus kx, where F is the restoring force, the unit is the Newton denoted by N. K is the spring constant, their unit is the Newton per meter. A measure is the stiffness of the spring. X is the displacement from the equilibrium position in a meter. The negative sign indicates that the rheosteric force is a opposite direction of the displacement. That means you stretch the spring positive displacement and the rheosteric force pull back its back is in a negative direction. Let us see the one example how we calculate the rheosteric force. Suppose that if you stretch the spring by 0.1 meter and the spring constant is the 50 Newton per meter, the rheosteric force, then the rheosteric force how we calculate? Just using the formula F is equal to minus Kx, putting the value of the K and X, and after the calculation we are getting minus 5N. That means spring feels the force 5 Newton in the direction opposite to the stretch, trying to return to its original length. Elastic properties of the matter. Elasticity refers to the property of the material that allow it to return their original shape and size after removal of the force causing deformation. The material that return to its original shape after the deformation is called the elastic material. Next, our topic is the stress and strain are the fundamental concept in the study of the materials under the mechanical load. These concepts describe how material deform and react to the external forces, and they are key to understanding the mechanical behavior of the material. In short, we can say that stress refer to the causes of deformation and strain refer to the effect of deformation. Let us understand the stress in a detail. Stress is defined as a force per unit area within a material that arises from externally applied forces, uneven heating or permanent deformation of the permit an accurate description and predict of the elastic, plastic and fluid behavior. Stress is given by the formula sigma is equal to F upon A, where sigma is the stress applied, F is the force applied and A is the area of force application. The unit of the stress is Newton per meter square. Type of stresses. Stress applied to the material can be two types as follows. First is the tensile stress. The external forces per unit area of the material resulting in the stress of the material is known as the tensile stress. Compressive stress. Compressive stress is the force that is responsible for the deformation of the material such that the volume of the material reduces. Next, our topic is the strain. Strain is the amount of the deformation experienced by the body in a direction of the force applied divided by the initial dimension of the body. The following equation is given the relation for deformation in terms of the length of the solid. Epsilon is equal to sigma by length, where epsilon is the strain due to stress applied and sigma is the change in the length. It is the original length of the material. The strain is the dimensionless quantity. It is just defined as the relative change in the shape. Type of strain. Strain experienced by body can be two types depending on a stress applied as followed. First is the tensile strain, that is also known as the longitudinal strain. The deformation or elongation of solid body due to applying a tensile force or state is known as a tensile strain. In other words, we can say that tensile force is produced when a body increases in length as a applied force try to stretch it. Next, that type is compressive strain. Compressive strain is the deformation in a solid due to application of the compression stress. In another word, compressive strain is the produces when body decreases in a length when equal and opposite force try to compress it. Strain and strain curve. Stress and strain curve. When we study solid and their mechanical properties, information regarding their elastic properties is the most important. We can learn about the elastic property. We should also know about the elastic properties of the material by studying stress strain relationship under the different loads in this and in all materials. The materials stress strain curve give a stress strain relationship. In a strain that curve, the stress and its corresponding strain value are plotted. The example of stress strain curve in a given below. Let us understand each portion of the graph. First is the proportional limit. It is the region in the stress strain curve that obey Hooke's law. In this limit, the stress strain ratio given as a proportionality constant known as a Young modulus. The point OA is the graph represent the proportional limit. Next reason is the elastic limit. It is the point in a graph up to which material return to its original position when the load acting on it completely removed. Beyond this limit, the material does not return to their original position and plastic deformation start to appear in it. Next, our reason is the yield point. This point is defined as a point at which the material start to deform plasticity. After that point past, permanent plastic deformation occurs. There are two yield points, upper yield points and lower yield points. Ultimate stress point. It is a point that represents a maximum stress that a material can endure before failure. Beyond this point, failure occurs. Fracture and breaking point. It is that point's straight strain curve at which a failure of the material takes place. Let us understand what is the elastic limit. The elastic limit is the maximum stress body can be experienced without becoming permanently deformed. If the stress exceeds the elastic limit, the final length will be longer than original. Ultimate strength. The ultimate strength is the greatest stress a body can be experienced without breaking. If the stress exceeds the ultimate strength, the string breaks. Next, our topic is the modulus of elasticity. The modulus of the elasticity is the ratio of stress to strain in the linear portion of the stress and strain curve in a material. The formula for that is the E is equal to sigma by epsilon, where sigma represent the strain and epsilon represent the strain. The unit is the Pascal, denoted by the Pa. Let us explain let's understand what is the significant are the modulus of the elasticity. High modulus elasticity indicate that material is stiff or rigid, meaning that require a large amount of stress to cause a small amount of strain. For example, steel has a high modulus of the elasticity, low modulus of the elasticity that indicate material is flexible or elastic, meaning it deforms easily under the stress. For example, rubber has low modulus of elasticity that have some application also. In a field of engineering and construction, use the select material for the structure application where stiffness is the important. Mechanical design help to designing components that need to the withstand specific load without permanent deformation. There are the different type of modulus. First is the Young modulus, second is the shear modulus, third is the bulk modulus. Young modulus. Young modulus is the fundamental mechanical property of the material that quantities their stiffness. It is the measure the ability to material to withstand the charges in a length when subject to the tensile or compressive force. This property is the crucial in engineering and the material science because it helps to predicting how a material will deform under a given load. First one is the definition. Young modulus defined is the ratio of tensile stress and tensile strain within an elastic limit of material. The elastic limit is the maximum extent to the which a material can be deformed without understanding parameters deformation, which is denoted by their mathematical formula for that is E is equal to stress upon strain, where sigma is the tensile stress and epsilon is the tensile strain. The SI unit for the Young modulus is the Pascal, which is equivalent to the Newton per meter square. Commonly, Young modulus value of the engineering material given in a gigapascal, where 1 gigapascal is equal to 10 raised to the power 9 Pascal. Significance of the Young modulus. Stiffness indicator, a high Young modulus indicate that the material is stiffer, meaning that required greater force produce a small deformation. A lower Young modulus indicate more flexible material. Designing parameter. Engineering used to Young modulus to select material for the application of the specific stiffness is required. For example, structural beam in a building must have high Young modulus to prevent the damage of the building. Fourth, under this Young modulus topic, there is the another topic is the stress and strain relationship. The elastic region, the stress strain curve, the relationship between stress and strain is a linear. This is where Young modulus is defined. First is the linear region. This part in a curve represents Hooke's law, where sigma is directly proportional to the epsilon, and the slope of the line is the Young modulus line, which is earlier we discussed. That have application in many more fields like construction material. In a designing building, bridge and other structure materials, we have high Young modulus like steel are perfect to the ensuring minimal deformation under the heavy load. Mechanical components. Mechanical components like shaft, rod and beams are designed considering their Young modulus to ensure They do not deform under the operational load. Material selection. Young modulus is the use to material selection to the compare stiffness or different material. For example, material with a lower Young modulus may be selected for the application requiring the flexibility such as the rubber band or a spring. There are some example of the Young modulus for the different material, like steel have Young modulus approximate 200 gigapascal, aluminum have 70 gigapascal, that is the approximate number. Rubber have Young modulus like 0.01 gigapascal. Shear modulus. There is the another type of the modulus. It is also known as the modulus of rigidity. The fundamental mechanical properties that describe material response to the shear stress. The measure the material's rigidity stiffness when subjected to force that causes of shearing deformation. Shear modulus defined as the ratio of shear stress and shearer strain within elastic limit in the material is denoted by the G. Shear stress tau divided by shear strain gamma, that is their mathematical formulation, where the force per minute area acting in a parallel to the surface of the material, which is the known as the shearer stress. Shearer strain is the angular deformation or change in the shape response to the shear stress. The unit, the SI unit for the shear modular is the Pascal, which is equivalent to the Newton per meter square. Significance of the shear modulus. Rigidity indicator. That modulus indicate how resistant material it is the shearing deformation. A higher shear modulus means material more rigid to and less prone to the shear deformation. Design parameter. Engineer used to shear modulus to analyze and design components that experience shear force such as a beams and fast and other part of the buildings. The elastic limit. In the shear state exceed to the elastic limit, the material may be undergo parameter deformation and the linear relationship is no longer applies. That have the application in many more fields like structural engineering. Shear modulus used to the analyze shear forces in beam other structure elements. This help to designing structure that can be resist shear, indicate failures, induces failure. Material selection. That modulus health is an important factor when selecting material for components subjected to the shear forces such as the bolts, rivets and the joints. There are some example of the modulus in different material, like steel have shear modulus approximate 80 gigapascal. Steel has a high shear modulus, making us suitable for the application requiring the high rigidity and resistance to shearing forces. Aluminum has shear modulus value approximate 26 gigapascal. Aluminum is the less rigid compared to steel, which makes it a more susceptible to the shear deformation, but still used in a lightweight structures. Next is the rubber. The value for the shear modulus is approximate 0.006 gigapascal. Rubber has a very low shear modulus, which is why it easily deform under the shear stress, making it ideal for the application requiring the flexibility such as the shock absorb or a seals. Bulk modulus. Bulk modulus is the fundamental mechanical property of the material that quantities their ability to resist changes in a volume under the uniform pressure. It is the measure of a material's incomparability and the essential for the understanding how material respond to compressive force. Bulk modulus is defined as a ratio of the applied pressure known as the stress to the resulting relative changes to volumetric strain of a material. That is denoted by the in a mathematical formula also pressure divided by volumetric strain, where pressure is the increase the pressure applied to the material. Volumetric strain is the relative change in the volume in the material under the pressure. The negative sign indicates that increase the pressure typically causes decrease volume. The unit of the bulk modulus is the Pascal, which is the also equivalent to the Newton per meter square. The bulk modulus value is often given in a gigapascal, like 1 gigapascal is equal to 10 raised to the power 9 Pascal. The some significant of the there are the some significance of the bulk modulus, like incomparability indicator. The higher bulk modulus indicate that material is the less compressible and more resist to volume change under the pressure. Materials which is high bulk modulus like metal are relatively incompressible. Design parameter. Bulk modulus is the crucial in a designing system where material are subjected to the high pressure, such as the hydraulic system, deep sea equipment and pressure vessels. Pressure volumetric strain relationship. When a material is subjected to a uniform pressure, increase volume decreases by amount of volume change, deformation in a volume. The bulk modulus define how much volume changes to response to this pressure. Let us recap the what we studied today. First we studied the what is the stress, strain and different type of the material modulus. First is the Young modulus, shear modulus, bulk modulus, type of the stress, tensile stress and compressive stress, what is the elastic limit, what is the ultimate stress. So, dear learner, hope you understand the all concept of elasticity related in our topic. In a next lecture, we will also study and discuss about the surface tension and their different phenomena. Thank you for your being patience.